Okay, I'm Dan Dessau from the Department of Physics. It's truly an honor to introduce John Martinis, today's CUbit speaker. John is really one of the major figures in quantum fields. So he's coming to us from UC Santa Barbara. Also has some startup companies, Quantala and Colab. As he told me, all companies in this area need to start with Q. So let's see. John got his PhD in 1987, working with Professor John Clark at UC Berkeley, studying superconducting qubits, some of the really early demonstrations in this field. He did a postdoc in Saclay in France with Michel Devereux, another major figure in the field, is at Yale now. And from there moved to Boulder. He had a great career at NIST Boulder I have it down, it was something like 18 years or so. From I don't know when it was.
1987 to 2004.
87 to 2004, he was here at NIST Boulder. From Boulder, he moved to Santa Barbara. So he's been a professor there since 2004. Of course, took on major responsibilities, formed a group, a Google group in Santa Barbara, where he moved his lab to Google, kept an appointment at the university, and this is where they demonstrated quantum supremacy. There's major news in our field. Along the way, he did many other things when he was at NIST. I guess he had just been thinking about really how to build the quantum computer, but before that, he developed this idea for single electron counting that became a new standard. NIST is all about standards, of course. Founded this new program measuring X-rays, X-ray energies using bolometry, using transition edge sensors from superconductivity. And those programs are still continuing to explode. He will tell us about his latest ideas. Super excited to hear them. So thank you, John.
Yeah, thank you. It's great to be back in Boulder. A lot of fond memories here. Yeah, so what's interesting in my career, I started with very basic experiments as a graduate student at UC Berkeley in the mid-1980s, and a career later, it's really fantastic that we have major companies having these big programs to actually try to build a quantum computer. It's kind of amazing to think that it was possible going back to some of the early talks trying to get this technology to work. And I just find it really fascinating going from, a very academic, just fundamental science way of thinking about it, all the way through to building a product. And what I want to do today, it's a little bit different kind of talk. I want to talk about that journey of going from science to a product. And I hope that will help some people. Some of the students probably will go into industry, help to it. I think I hope help you all to become better scientists too, because I think it's a little bit different way to think about developing technology that I think would be very interesting. So part of what's happening, so exciting, is quantum computing is now in a systems era. We're building these big systems. And the purpose here is to really think about how you want to think about systems. It's different than as you think about doing a fundamental science experiments. So what are the principles that you have to understand? I'm proposing here. And I would say the nice thing that you learn about this is to do better system engineering, you really have to do better physics and clearer physics, communicate better. And I think that's a nice conclusion to bring out of that. What I would say is I've been very much influenced in this journey by the book 0 to 1 by Peter Thiel, which is all about startups. It's really, really great. And also about systems engineering. I did read this one book, which I thought was really clear about how some of the differences are. Again, I'm putting the science spin on that. So here's the outline of the talk. The first thing I want to do, surprisingly maybe, is to tell you that the scientific method is not really good for systems engineering. So I have to explain that. And kind of with that as a basis, I'll go through and talk about some of the key concepts and principles you need to think about this. I'll give examples for what we're doing with superconducting the qubits. And also at the end, I'll talk about specifically on quantum, what are some of the challenges here. But there's a series of principles here that I think will be interesting to learn about. Okay, so I make the statement, the scientific method fails. So the scientific method, and I'm going to follow this book that I quoted in the first slide, is where you specify what you want to do, you design it, you build, test, and you feedback and go over and over again. So that's a simplified view of the scientific method, and that's mostly what you do when you learn to do science, both in grade school all the way up to high school and as a professional physicist. And one of the interesting things about this system engineering book is he kept harping over and over that this scientific method is known from experience to cause technological projects to fail. Okay, that really surprised me because you think that the scientific method is just really important. And it is, but you think about problems in the wrong way. And it took me a while to understand that. I don't know if I'm going to explain this well, but the traditional ad hoc endless loop, we call it plug and chug, engineering wanders around inefficiently and ineffectively performing activities. You're doing things, but they're not efficient. Then when the system goes into system integration, tests, and evaluation, that's for a big, complicated system. Incompatibility and interoperability emerge, poor design iteration, quality of latent defects is very high, significant costs and schedule overrun. Okay? So, what does this really mean? And again, this is well known in the systems engineering literature. So what's going on here? So basically, this scientific method is a workflow. But what you really need in doing all this is better decision making, better organization, better knowing what projects to work on. And another way to think about it is there's an infinite number of research projects that you can do. But what you want to do is focus on the end goal product, okay? But then, of course, you need data, which you're kind of going to get from here, but you need data to do data-driven decisions and move forward carefully. So it's really you have to be a much more thoughtful approach in that. And I'm going to help to try to define that as I move through my talk today. What does that really mean? But this is a big principle. It's like you have to rethink how to do things better. Okay, so the first thing you want to do is what's your mission and focus of your project? So, and as a graduate student, it's all about writing papers, right? Or maybe more generally, do research, okay? And if you talk to the PI, they'll tell you the real purpose is to get more funding so you can keep going over and over again, right? So it's all about funding, okay? You have to fight that thinking. That's bad thinking. Of course, you have to keep getting funding, but you have to remember, what you're thinking. And I would say for building, let's say at Google, the first thing it did was come up, okay, what's a short statement of what we want to do? We want to build a useful quantum computer, okay? Now, when we did the quantum supremacy experiment, that was not useful yet. All we did was build a powerful quantum computer. So, we didn't really fulfill this yet, but it was useful in the sense that once we did that experiment, then the group was given a lot more funding to build a useful quantum computer. So it was useful going up to the original statement. Okay. Now, this one thing you have to do when you have this, okay, build a useful quantum computer. You can do that a lot of ways. Okay, so you have to build up, how are you going to organize your thought? What are the important things? So the first thing is to figure out what the critical issues are. And what happened for me is at some point we wrote a paper on doing error correction with the surface code, certain architecture. And once I read that paper, I could vision in my mind what actually we had to build. Up and then it was just a bunch of qubits, I didn't know. But that was a really important paper for me. And it basically said that you have a 2D, like a checkerboard, nearest neighbor architecture, which you could do on a chip, okay? And then it told me something about qubit specifications and how we would have to build the chip. And once I understood that, which is kind of a systems approach of how to build everything, then we really knew what to do. And we were able to make actually rapid progress doing that. And specifically for the qubit specifications, it's the qubit errors that are the most important thing. And what's funny is I go to conferences and hear things, a lot of times people talk about magic qubits, which are qubits where you can just run and you're going to get an answer out of them. Let's say you do a quantum simulations, and they never talk about error rates. And we know qubits are fundamentally error prone. You have to make them good in order to do anything useful. And somehow, why is it we're not talking about it? So this is something that I thought about very early on, which was happening. For example, there's this idea using matrix product states that you can efficiently simulate some kind of quantum program that you want, but that approximation of a matrix product states will give you errors of order 1 or 2%. So it means if you build a quantum computer that has of order 2% errors, then you might as well just run a classical calculation of matrix product states and get the answer. And maybe it won't always work or something, but it tells you you have to make a quantum computer good enough just to beat good classical algorithms, okay? So that tells you, you want to be better than 2%. And the errors, if you want to do a powerful quantum computing, has to be about 0.5%, 50 qubits. If you want to do near-term quantum computers, you maybe need errors in the 0.01% to 0.1% with maybe 100 qubits. And if you want to do error correction, you need less than 0.1% at 1,000,000 qubits. But anyway, you kind of have a feeling here of various levels of complexity, what you need to build. And that helps you understand, you know, what is it that you have to do in the technology and what you have to focus on, okay? And in fact, the difficulty here is to get to scale a bunch of qubits, but also to get low errors. And in fact, in my view, for the field, low errors are the absolute key important thing you have to work on. And again, that's very useful from a systems point of view to know, you know, when I open a paper, what's the first thing to look at, to know if they really made an important contribution. Okay, so let's talk now about the intellectual structure of how you organize things, which we can call the stack, but it's a three-dimensional stack. Okay, so that's what's kind of interesting about this. Now, the obvious dimension is that when you think about your quantum computer, you start out with, let's say, the qubits, a chip you make, and then you have to put it into a chip mount, and then you have to wire up that chip mount to some hardware electronics. Then you have to have firmware that controls that, and then you have to build interface software and control software and calibration on top of it. So you can break it up into a stack, and then you can assign different teams to that stack. So that's the obvious thing. You need to do that. It's actually not too hard to envision what the stack is. It turns out the interfaces between the stacks is where all the problems are. I'll get to that a little bit later. However, I want to talk about two more kind of directions. Yeah. A stack? It's just a stack of these. It's very well known when you talk about like a computer architecture, that you have a stack of sub-projects that you have to put up, okay? And that you organize your program according to that stack. Now what I want to tell you is, besides that hardware or software, you want to think about the stack in terms of abstraction levels, okay? So, and communication levels. What does that mean in abstraction levels? That means as you describe how your system works and the various elements there, at each level of the stack, you have to describe it both in a very deep, proper, you know, really good physics paper, all the way up, maybe in several levels, all the way up to a very simple way to talk about a qubit, okay? So, you know, as physicists, we know qubits very deeply what's going on, but we want to talk to your spouse and you say you did something in a qubit, you wave your hands and talk about that. Now, why do you need to do that? When you're working on a big project, you're not just working with all physicists. You have physicists, you have software engineers, you have hardware engineers, and you need to kind of tell everyone what's going on in the full project. But you can't go and explain the detailed Hamiltonian to a software engineer. They're never going to understand you. So you have to have abstractions where you describe it in a more simple level so that people at different layers of the stack who are working on the project can understand roughly what's going on. And then you also, of course, you have the deep thinkers about your particular subject where you can, you know, make sure you're calculating everything right. And creating those abstractions that are both, you know, accurate enough, but clear enough is actually very difficult. And I would say one of my heroes in physics is Richard Feynman, who was able to do that, you know, describe physics at a very deep level and also kind of an approximate level so that people can understand. So you need to do that too. And then finally, you need to talk about what your goals are versus time. Think about your stack and time. The first experiment is this, then we're going to do this and this and this, building upon each level. And that way you can have a long-term project to test whether you're making things properly over time. So it's an organization of how you're going to do your science and technology development, not just the hardware, software, but in terms of your communication and in terms of your organization versus time. And that's, I think, very important to have a clear view of that over time. Okay? Now, I'm going to give some examples here. Okay? So I'll talk a little bit about superconducting circuits. Superconducting circuits are nothing but an inductor capacitor resonator, oscillator, with a frequency 1 over square root of LC, like you studied in your physics and engineering classes. The only difference is the inductor is not a physical inductor, but it's a Josephson junction, Josephson tunnel junction, which is a nonlinear inductance. And it turns out that when you look at that oscillator, you can map it to a harmonic, a pendulum swinging back and forth. But you know with a pendulum, as you swing to very high amplitudes, the frequency goes down. In fact, when it gets near the top, the frequency will go to 0. So basically all, and this is great, you know, you're having a complex thing. You talk to the electrical engineers and you say, this is nothing but a nonlinear inductor capacitor oscillator. And then from that, you can understand a lot about what's going on. So for example, if it was linear, it would be an energy versus, you know, phase. It's kind of like the flux in an inductor, parabola, and then it's going to a cosine potential because it maps to a pendulum. And then if you look at the oscillation frequency versus the energy in that oscillation, it starts out at the LC frequency, and then it goes down to 0 as the energy takes it up to the inverted position. And you can describe the quantum mechanics in a very simple way by saying, look, we know in a harmonic oscillator, you're going to have quantized states of 0, photon, 1, 2, 3, okay? And then if you take, and which are going to be spaced by h bar omega 0, this is, you know, electroengineers generally learn a little bit about quantum mechanics to understand present-day quantum devices. And then all you say is, well, as you have more, in perturbation theory, you say as you put more energy in the system, the oscillation frequency goes down. So you can map out what the oscillation frequency is for the 0 state, 1 state, 2 state, 3 state, and it's just a nonlinear oscillator. And that means the transition energy between 0, 1 is a little bit bigger than between 1 and 2 and 2 to 3. And it turns out that actually predicts the frequency to first order. So it's a good way to think about it, okay? So this is a way to explain in a simple way without having to go into all these Hamiltonian physics that the engineers may not want to know about, that it's just a you know, nonlinear oscillator. And that's how you're building your qubit. The other thing I will mention here, which I think is kind of fun, is talk about how you think about a quantum calculation as compared to a normal digital calculation that is going on in this computer, you know, billions of times a second, okay? And the basic way you think about a normal logic operation is you have a memory storage unit called a D flip-flop. So when an electrical signal here goes on an edge transition goes high, whatever is going on, whatever state is here gets transferred to the output. Okay, and then what happens is when that changes, that information goes back to your logic, say you're building an adder, and then adds the two numbers and sets it up here, and then the next clock cycle you get the result. And then it goes on as a state machine. So that's, you know, that's basically how digital logic works. Now it turns out in the quantum system, when you think about error correction, you can use that, kind of use that analogy to describe what's going on here. You have a qubit with the logic kind of built into it, okay? And the only difference here is that here there's an external clock, but here in the quantum system, remember it's this oscillator, and there's this self-clock of the oscillator going around in time, okay? And that all the computations are somehow synced with some external circuitry to this clock, okay? Now the problem here is there's errors in it, so you have to do error correction, kind of like what you do with classical error correction, and you decode the logic in some way. But the more subtle thing is that the clock that's running here can be, it's a different clock than a standard clock coming into all the gates of the D flip-flop. So those clocks can be operating at different frequencies, and you're going to get a phase error. As well as a logic error, you're going to get a clock phase error. And what you do, of course, is you do some encoding so that you can measure if you're making a clock phase error, and then kind of reset the clock to the right value using your error correction. So you just have to do error correction both on your clock and on your logic. Okay, so it's a good way to understand very simply what's going on there. Of course, that's a pretty high-level, simplistic way, but it does give you some idea what's going on there. Okay, so let's go on to the next subject, and I'll talk about this as inductive and deductive reasoning. Okay, so there's two kinds of kind of reasoning we use in science, and the deductive is what we're really used to in physics courses, where we start out with some first principles, F equal ma, and then we derive everything from that. And for example, in superconducting qubits, we have a Hamiltonian of the transmon, and from that we can deduce all its behavior by integrating the Schrodinger equation. So this is where we want to be. However, in whatever we do in science, especially when we do in the lab, there's a lot of things that we'll call inductive knowledge, where we kind of know it works, and we kind of maybe understand how it works, but we don't necessarily understand it in detail. And this is kind of what happens in the first experiment, or what works over time. And for example, if you look at superconducting qubits we're talking about today, tantalum metal is supposed to be a much better metal for making qubits. Okay, there's a paper on that, but we don't know why. Okay, we were talking today, why is it that? So because what happens over time is that you want to make the inductive more deductive, and that's what we do as scientists. We try to bring this up here. And things like the clean room fabrication, yeah, we do it a little bit, but a lot of times it's just a recipe. And then when it's quantum, usually we can get pretty close, because this is based on some good principles. So we're trying to move up in the scale over time. So kind of roughly you can think about this is when you do science, you basically come up with some ideas and demonstrations, which at first is a little bit inductive, but then over time you move up in here and it becomes a recipe and really good theories and models, and you do system tests, and you kind of know about reliability, and maybe even at the end you understand it so well that you can reduce the cost and make it useful. Okay, so this moving up in knowledge, if you like, which is what you want to do. You can't always do it. Clean room, you're never going to understand everything. Okay, but you try to do that. This is known as a technical readiness level. And this is a chart from NASA, where you see at the very top of the technical readiness level is launch, okay, where you launch something, which makes sense, right? But there's a lot of things we have to do before there. And basically what you're doing as you're going up the technical readiness level, you're just testing it and making things really predictable. And that happens in the lab all the time. We have some initial phenomenon, and then we use it over and over again, and we come to rely upon it. So this is kind of a practical tool that we knew about it. So the point here is, in order to predict, this is not necessarily the standard scientific method. We have to build good models and test systems and whatever, but that's what we need to optimize and scale. And the next thing I'd like to say is we tend to overestimate something as some knowledge that we understand first principles, deductive, when in fact, a lot of times it's just like, well, that's the recipe, okay? And often what you have to do as a scientist is ask, is this really a recipe, or is this something we want to know? And we were talking today about superconducting resonators. where that was kind of the argument I was making is I think, we think we're up here, but we're really down here in terms of our knowledge. We have recipes, but we don't know. And as a systems engineer, if you want to know where technology readiness level you are so that you can build something complicated, you really have to know that and be very honest about that. Okay, so software is an important part, and I would say that's one of the most interesting things I learned about going to Google is that there was, a big emphasis, rightfully so, to try to turn whatever you did into software, because then software could be automated, it can be changed easily, you can maybe predict and model things from that. It's a really powerful thing. That's what you try to do. Well, not everything can be done that way. And if you're going to build hardware, you're going to need a step-by-step recipe, okay? And one of the things I would note in graduate school, you tend to have experts who can build things, but no one is writing down what that recipe is. And as a professor, that really, bothers you at times, because once the student leaves, you wonder how in the heck you do anything. So of course you try to put that in the paper as much as you can, but really your documentation is very important. What I've learned in my career is I tend to reuse my designs over and over again, and I spend a lot of time documenting what I'm doing. Even if I like, I have a favorite screw that I know that works, you document that somewhere so I don't have to spend 20 minutes finding it 2 years from now. As I said before, the stack is easy. The interfaces are subtle and critical, and that's because when you have an interface, there's people above the interface and below the interface who want to optimize their system based on that interface. So they want to make that interface closer to them. So there's a natural fight between the people how to do that interface. And you have to work really hard to figure that out and make sure that over time, that interface is still going to work with you properly. And if you're working on a project by yourself, that's easy to argue that in your mind. You have teams, you just have to be more careful about that. So I'm going to also say reliability is the key to scaling. So good specifications and documenting, you have to do a lot of testing to make sure that it's working right, because the people above you are just relying on the testing to know what happened below them. Expert code review, very important for software, and then also continuous software testing of the system. That means like every day people commit to new software, they run global system tests of the software to make sure no bugs were introduced, which means you need to have good simulations of what's going on. Doesn't catch everything, catches a lot, but these are standard practices for doing systems. Okay, let me talk a little bit about clean room fabrication. Okay, clean room fabrication is the most inductive, it's really hard, and you have to really think carefully about this. These people are never appreciated enough, and it's doing hard. You work for a long time doing boring, repetitive things, and then you see if it's gonna work. Whereas, changing one line of code and recompiling it is pretty much instant gratification as to whether you got it to work. So you have to think very carefully, and you have to make it easy as you can. You appreciate them. You have to reward people who's we're really working hard on that. So you have to integrate these very carefully with project goals. How predictive is your fabrication? Okay, and I would say what happened at Google is that we made decent qubits, 15 microseconds, and then we went ahead and built this chip for quantum supremacy, which is very difficult in terms of control. And we just didn't worry about coherence, and we got things to work, and it was great. And then in the end, of course, you want to make it better, but it was such a complex chip, so many different interfaces and wiring, whatever, that it was very hard to know what was wrong. And what was really challenging there is to go back and say, well, what predicts, why is it having this performance? So you really want to work that. Now, what's interesting here is there's a mental change when you go into production. Okay, so there's the research and development change, and physicists are really good at this because they want to change the process and continuously optimize, and that's really what you want to do. And if you have a recipe, they just cannot help themselves to change a little bit, run the run. It's impossible for them to stick to one recipe. It's just not possible for physicists. However, if you go into production and complex devices, what's nice is you then hire technicians, and they're much better infinitely better than physicists to stick to the recipe. And okay, if you need to check that, tell them, let's do an A/B test, do this, do that, we'll check it. And they'll be able to do that. So you do that for maximum reliability. However, because they're not observing that, for research and development, this may not work, okay? So both of them are useful. You just have to decide where you are. And some of your people should be doing this, and some of your people should be doing that. And as a system engineer, you have to kind of figure out where you are and optimize that. So it's really interesting to see this happen in practice. That was something that was great. And then at Google, we started hiring technicians to do the fab. And of course, that took time off from the physicists, but they also were able to do it. Oh, one last thing. You shouldn't automatically think that hiring technicians and process engineers is great. Because if you have a bad process, all that'll happen is that you'll get really good at building mediocre devices consistently. Okay, you don't want that. You want to improve it. So you have to hire more than normal process engineers. Okay. So let's talk a little bit about leadership. The job of the system engineer, project engineer, is to maintain intellectual control of the problem solution. That's kind of the stack I was talking about earlier. But you have to understand all the concepts. Otherwise, this scientific method paradigm will prevail and lead to confusion and chaos. This is from this system engineering. And the focus, this is the best quote of all, the focus is on making timely and informed technical decisions instead of producing documents. Okay? Really understand what you're doing, making good decisions. So when you want to do decision making, the first thing you do is not treat this as a Twitter thread where you're only arguing your point of view. Okay, and so we're all so ingrained to that, you just don't do that. What you have to do is talk about it in terms of the pros and cons, okay, by each side. And I would say there's a general rule, you ignore any pitch without talking about anything that can go wrong. It's just too one-sided. And again, you're used to this in social media, Twitter, just no, don't do that. That's wrong, okay? And you have to argue ideas, and then you have to gather agreement. Even if it's going to be wrong, thing, you have to move forward. Typically, system engineering is about one person in, 7 is a system engineering, kind of program manager types. And I'm going to say the last thing is, if all your projects in the stack are assigned without supervision. Okay, so I'm going to say this is an academic style where you have each people doing their own research for your whole project. You sign that out, and then you see what happens to it. There's a problem with that. So let's say you have 50 critical tasks that you need to do, and you sign it to 50 people. Then you have 50 single point failure points, 50. And not everyone's going to work. Okay, you know that. Some people will need more help. Some problems will be so hard, they need a lot of help. So, you need to have the system engineering leadership to make sure that everything is moving okay. Okay, and that's not the academic style, by the way. That's different. Now, one of the things, I'm going to talk a little bit about quantum computing now, is if you think about doing error correction, one of the ways to think about that is, what are the requirements for doing error correction? And the thing that happens when I read papers these days is there's a certain body of knowledge where we are right now, and you're going to do an error correction experiment to push it a little bit more in this direction or that direction, with this idea or that idea. And this is the scientific method. And according to system engineering, this can lead you to systematic failure, project failure, disaster. And the reason being is there's a lot of things you have to optimize at the same time to do something complicated. So for example, in error correction, okay, this is for a particular case of the surface code. There are certain system requirements. This is a partial list. It's a big list. And you have to make sure that you know what your threshold is for errors. You have to know what physical errors you need, and then how many qubits, numbers per, how many physical qubits you need for a logical qubit for some small error rate. You need to know the connectivity. You need to know if you're going to error decode this. It's very complex, and you want to even know if a supercomputer can do that. You don't know that. Some of these errors, some of this error correction codes, you can't do it. So, why are you working on that code if you can't decode it? Okay, you can think about that ahead of time, right? And then, okay, when you have single logical gates and CNOT gates, the logical gets more complicated. This is nice because it's braided, so it's an interesting, simple mechanism. How you get a measurement? Can you do things in parallel? Can you do long distance? There's something called T-state distillation you need. It's very complicated. There's an overhead from that. There are correlated errors. A long list of things. There's probably, 10 times as many things when you get into the detail. And the point is, and from the system engineering point of view, you have to think about this well ahead of time to make sure that whatever path you're choosing, you're going down something that will work, or at least will likely work, or at least if you know the things that you have to fix, you know what to fix. And when you're doing regular scientific academic research, you're just gaining knowledge, and that doesn't matter so much. But if you really want a product to work, you have to think about that. Okay, testing and reliability. When you do a physics experiment, you work very hard to get it together. It finally works. Maybe check it again, make sure it's okay. But typically, that's the last 10%, and then you go off and run write your paper, okay? And then you might use it again, but you're done there. It turns out that for system testing, it's not the last thing you do. It's about 40% of your effort, and you're doing it all the time. 40% of your people are testing the weather to make sure you're doing it right. So this is great because it'll tell you if you understand the fundamentals. You test subsystems, and then full system tests. You test all the interfaces. You detect and localize each fault, not just identify, right? You want to make sure you understand how everything works. And reliability is a part of development because it's super expensive to fix. So you want to catch it early. And I really like this number 6. You want to get user data to discover vulnerabilities, and it's called blind testing. So the example here is that people put their quantum computers in the cloud for outside people to use. And Amazon, for example, has a very nice service to do that. And what are you doing it? Well, because the outside users are testing it, and you're learning if there's things that are going wrong that you hadn't thought about. And the users will use your quantum computer in ways you hadn't thought about, and maybe it'll break and maybe it won't, but you're going to learn a lot from that. So this kind of blind testing is very important. And for me, this is like, you know, you want to go from, you know, Kitty Hawk to the Saturn V, go to the moon. You know, you have to have, you know, do a lot of user testing on the aircraft and spacecraft in between. Okay, so this is really good that the field is doing this. Need more of it. Okay, so now we're going to talk in the last few minutes about quantum system engineering, talk about quantum devices specifically. And, you know, when you build a qubit, you have to have, you know, good coherence. You have to be able to couple qubits together, good measurement, low errors. And these are kind of competing requirements. If you want good coherence, as I often say, you should choose neutrinos, right? They're going to have a very long T1 time. Of course, you can never build anything out of it. So I always ask when I see a new proposal, is this qubit neutrinoized? Okay, if it's neutrinoized and you can't make 2 qubits out of it, not so good. The other thing that's really interesting about this is that you need good control for every qubit. Okay, these are actually analog processors, which we kind of use through measurement, give us digital kind of answers and error correction. But you know, they're really analog control, and you have to reprogram, flexible architecture, scalable, maybe make it general purpose. This makes it hard. So what's really so hard here is this ability to control. And the way I like to think about this is when you build a standard CPU, you have a central processing, some memory, maybe internal input devices, output devices, but you can copy information. So if you have information from here to here, you just put it on a bus and you copy it. No problem. And that means once you define that interface, this group of engineers can design it differently than this and this and this and this, as long as the interfaces are known. Now the problem with qubits is you can't copy information. Okay? So you can't build these general purpose interfaces. Now you can transfer information, but you have to think about how to do that very carefully. And the real problem is that means this group of engineers here are going to be talking to this group about how they share this valuable qubit resources, and they're going to fight, you know, to get more than their share to make their job easier. And it's the compromise of that interface that makes it very hard. And of course, you have many, many things here. So it's really makes it separating into subfunctions at the qubit level kind of difficult. Okay, and you really have to, you know, work. That's why system engineering is even more important. So let me give you an example here on information constraints on control. I have a small archive paper that talks about this. So we have a bunch of qubits. Remember, these are analog control, so they go up to a control system that programs waveforms to control the qubits and do all the logic. So that's basically how you have to do it. What you may not understand is that for each one of these lines for a qubits, and this is at UCSB, it was more at Google, there's about 100 or more parameters per qubit that defines what's going on here. If you want to really optimize the error, there's a lot of parameters. And there's a lot of information complexity involved in, of course, you know, a lot of physics involved in turning those parameters into a waveform. Okay? So that's a lot of information, and basically that means you have large area and volume CMOS in a control system. And I'm going to say generally for qubits, you have quite a bit of number of parameters, and that means your control system is large. So if this is large and your qubits are submicron, how are you going to wire it out and do all that? Okay, so large qubits are good because it kind of matches to the requirements of your control system. Not a hard and fast rule, but it's just something you have to think about. Now, you're going to say, well, why don't you just build a more clever control system to simplify the control? Okay, and multiplex and do something like that. We do to some extent. However, to do that, generally, when you try to simplify control, you're not going to control it quite as well. And that means you're going to have higher error qubits. And that's the last thing you want. You want to make the low error qubits. So low error qubits does not really, it forces you not to do this kind of thing because you don't have the engineering margin. These are coupled together. So low qubit errors and simplifying control. Now my hope is that we can improve materials, make qubits better to get way below this, and then we can start simplifying our control and making the control system better. But these two are talking to each other in a very subtle way. And one has to think about that as a system engineer to figure out what that compromise is. Okay, so almost this is, I think, second to the last slide. So system engineering for quantum computing. Okay, the first thing, physicists are bad system engineers. You're born and bred differently than a system engineer, okay? Remember, as a physicist, you want to isolate some physics phenomenon, throw away the rest of the world, isolate, say, that one or two variables, and figure out what's going on. As a system engineer, you have to build a complicated system with hundreds of variables. You just do things differently, okay? So you really need to think differently. Big change from research. You need research transformation, need your overall goals, and understand your end system. You need clear concepts to interface and optimize, not just a detailed paper, maybe 1 or 2 page summaries about the length where people can understand. New and a complex technology needs to explain to the entire team, okay? So abstraction layers of physics and milestones. Calibration, metrology is a super important issue. I was really happy as to work at NIST to really understand that. Spent a lot of time figuring out the right metrology. Control systems, alternative information problem. And finally, there's this idea that you want to talk about how your qubit system is the best in the world. There's no problems, we're going to get it to work. I understand we have to be optimistic, but what happens is if you advertise problems, then people will think about fixing it. And if you don't advertise your problems, my guess is people, even internal to your team, won't spend the time to fix it. So, to me, I really want to hear when people, talk about what they need to do, because that's how you're going to fix it. Okay, so yeah, this is, I think you can read this. System engineering has a good template. We have to think differently. And I'm going to say, scale with software, lots of testing, how predictive is your knowledge? But all of this, I really like this because all it says is in the end, we need better physics models. You have to be really critical about what you know, do a deeper physics understanding. And we all want to do that. That's a good thing for us. And I hope this encourages people to do the better physics. And finally, I'd love to discuss or learn from other people at the High Ideas. I think it's a really interesting project, and I think it's an idea, and I think this is what's really needed to build this super technologically challenging object called a quantum computer. I'm optimistic we can do that, but I think we have to think much more deeply and carefully to get there. Okay? So thank you very much for your attention and time.
Okay, well, thank you so much. Questions? Yeah. You wanna?
Hey, Joe.
Hey, John. On the previous slide, you had a really interesting point. The last point, need to advertise problems is the only way to fix. So this really runs counter to academic instinct because you have to raise money. If you say you can't do a thing,
Oh,
it's bad.
by the way, it runs counter, especially counter to startup companies and especially counter to corporations.
So I was going to ask you,
Everywhere.
what ideas do you have to fix that last problem in particular?
Yeah, I don't know. I don't know what you need to do. I put it up there because it is a conundrum, and I would say this is something that has hurt my career because I have talked about the problems in a way that maybe make people uncomfortable. So I have to learn how to do that better. But my feeling is if you don't do that, the long-term prospect is not good. Now, for example, I really like the fact that China, and China only, has reproduced the quantum supremacy experiment, which is not about showing a powerful quantum computing, but actually error budgeting your qubits. That's what that experiment is about. And it's the only group in the world, other than what we did at Google, who wants to know if the errors of their qubits get worse when you put it in a big algorithm. And I give them lots. I think they might be the leaders in superconducting qubits even, because they're thinking this way. And so I'm really worried about China, if they're really thinking in this way. And when I read their papers, it's very clear they're trying to do the metrology. So yeah, you work at NIST. Is metrology important? Yes. Okay, and knowing that maybe your system doesn't work as well as you thought is bad, but we have to get over it. I'm going to say also that I think my generation being older, think Apollo 13 and failure is not an option generation, that was a little bit easier than it's now. And I try to encourage people to be a little bit more this way. I think it would be good for physics and, bring the level of competence up. Thank you.
Thank you for this. Can you hear me?
Yeah.
Yeah. Thank you for the great talk. And I think I agree with your general premise that, to build something useful, you need this systems engineering approach. But I think there's also maybe an issue with doing systems engineering too early in the technological development stage. So say you have, as it is now, you have multiple hardware qubits competing for what will eventually be. And say, there are like 15 companies and each of them spends billions of dollars building up their technology stacks, like you said. And then in the end, only one succeeds. That seems like a lot of wasted money and effort in some way. Isn't it better to, do it in a more physicsy way where you start from fundamentals and then do like an exploration of all these things, and then when something works, when you're sure at some point that something works, and then you start building these systems around that. Could you comment on maybe why that isn't or is
So
the way to do things?
I'm sorry if I didn't quite understand the question, but I think I might be able to answer it this way. I think the only way to know whether all the different approaches will work is give people a chance to build it and see if they can overcome all the issues and do that. So I think that we're in a good state now where all these ideas generally are getting funding. We're finding out what's going on. There are pros and cons to different things. So I think we're fairly in a healthy environment right now. What I think is unhealthy is exactly this comment. If I want to know how well your qubits work, whether they're errors, what happens when I put a lot of qubits? Do the errors go up? The system errors go up? That is being avoided generically, and I would like to know that, just to be able to see if people are actually making progress. That's the way I look at it. There's probably lots of other ways to look at it. So I don't know. I hope I answered that question. It's hard. There's a question here. Thank you.
Yeah, so Google has its 53.
Can you lower your mask for a second? I have very bad hearing. Thank you.
Okay.
Just for a second.
So like Google has its 53 qubit device, and IBM just released a device with like 400 qubits. So from a system engineering perspective, for devices at this kind of scale, what is the most difficult part?
Okay, I didn't quite catch the whole question, but I think I can answer it. The IBM machine has errors of about 1 or 2%, and I think it's even worse when you do a big algorithm. Let's say you had 100 qubits, and you have a 1% error. That means in one instruction set of 100 qubits, you're likely to see one error. Now, maybe you can get to 2 to 3, and some fraction of the time, you're not going to have error. What algorithm are you going to run with 3 instructions? So my huge complaint, and I say this all the time, and thank you for saying that, is what does it mean to build large qubit systems with these kind of error rates of 1 or 2%. Now, there are people now, for example, building neutral atom quantum computers that are large, but they don't even know what their errors are. They haven't measured them yet. They're doing some interesting phase transition stuff, and it's certainly great. But if they don't know their errors, I have no idea to know whether this is a viable quantum computer. And if they're not doing something that you can't do with matrix product state. So my statement here is this whole metric of how many qubits you have is completely meaningless at this point. The true metric is, for a modest number of qubits, 10, 30, 50, 100, what is the error per qubit? That's the true metric. Forget about quantum volume, forget about all these complicated measurements. Just tell me that, and measure that not with 2 gates, but measure that when you're in a big quantum computer. So for me, that's what the field needs to be more honest about what's going on. And I'm going to say the real reason people aren't reporting this is probably due to the fact that those numbers aren't very good and they don't want to talk about it because they're worried about losing their funding. Now, I know they're working on it, and that's great, but you should do it. Now, obviously building a 400 qubit or 1,000 qubit is a big achievement. That's hard to do. But I think if you had 10 qubits at 0.01% errors or 30 qubits at 0.01% error, that would be way more exciting for the community. And I think if you did that, everyone would say, oh, okay, you can get small errors now. I think you just have to scale up, but you're not enough scale that maybe we can do that. And that would be the breakthrough that we need in the field. And by the way, my company, that's what we're trying to do. No surprise.
I was just going to ask that. How soon do you think that might happen? That level?
I think if you got lucky, you could do that in 6 months to a year. If you really we have some ideas on it. Probably 0.1% is that time, and maybe 0.01 would take you a couple more years. I think it's possible in superconducting qubits to get there, and we have a bunch of ideas to try to figure that out. But okay, we have to do it. I'm optimistic like everyone else. Okay, fine, fair enough.
Yeah. You have to put in the context of, you mentioned 1 or 2% error rate. What is in comparison? The Google Google chip?
The Google chip was about 0.5%.
0.5%.
0.5%, and the other ones are 1 or 2%. So,
Okay.
but it's 0.5% when they ran the whole thing. If you wanted to know our best, it was 0.1%.
I see.
But which is what everyone tends to quote. Or let's say on 2 qubits. Yeah, you can make that great. But
Like
this is 0.5% average on a big chip.
Okay.
And that's hard.
Thank you.
And in fact, that when that happened at Google, that totally surprised me that it worked so well. I was expecting lots of things to go wrong. But we did work very hard to try to get that for many years. And the Chinese have reproduced this, so it's, that's good.
Hi, John. Can you talk about some of the metrology that you think is super important for this field?
Yeah, so the metrology, yes, so the metrology basically for me is qubit errors. Okay, and I have a talk on that, that I don't have a slide that I can bring up. But you start with things like T1 and T2, which are standard qubit measurements, and then you need to know your gate times. And those ratios kind of tell you how good your error is. And you have to measure, let's say, a single qubit error and 2 qubit errors on 2 qubits. So that kind of, and then you have to do that with a long sequence, which you can do with something called randomized benchmarking, which I think the first thing was done in Dave Weiland's group at NIST here. And everyone's doing it. And that way you make sure that the errors are low, not just when you do one operation, but when you do 1,000 operations. You need to know that. So that's if there's any time crosstalk in there, memory. And then once you do that, you have to increase in space by making a lot of qubits and make sure that when you do a lot of qubits, your errors don't degrade. And for example, the cross-entropy benchmarking is one way to do it. There are now other ways to do it so that you can do that, on 30, 40 qubits, 50, almost 50 qubits pretty readily. And there's other ways to do it. So then you do that. And in this case, what you do is you measure the average error per qubit operation per gate. That doesn't tell you the full quantum matrix of what's going on, but at least gives you some idea of that. And knowing those errors, if you do a new algorithm, you can kind of estimate what the total system fidelity will be for that new algorithm. And that's what's useful about that metrology. So to me, there's a way to build it up. People might build it up in a different way, but we kind of know how to do that now. And I would say that the quantum supremacy experiment, in my mind, being an ex-NISTer, that was a metrology experiment. And I wanted to know if the thing screwed up when you built a big system. And that experiment tells you through all that. And it more or less, agrees how you, it more or less says it has a total system error rate as you would expect, which was really surprising to me.
John, so given that you think system engineers are so important and physicists are bad system engineers by their nature, what is your vision on training good system engineers for quantum computing in the future, especially in a university setting?
Yeah.
Or maybe another quick question, where do you get good system engineers in Google and your companies right now?
So I was talking with someone just before now, how at their company they had system engineers who came in, say from the aerospace industry, and they weren't able to be very effective to help the quantum physicists at all. Now, I think as you get more mature, those people can come in. But given the complexity and the amount of interaction between the different technologies that you're building, I think it's more likely that the system engineers have to come from within the quantum space because they're going to understand a large part of the stack and know how to do things. Now, when you build a system here, you'll have a system engineer who'll be for software, who might be for hardware, and that's all great. But you have to have someone thinking about the whole thing, to do this. So I think it's going to come from the physics community, and I think it's going to be some small fraction of the physicists who find this kind of thing really interesting and can kind of train their mind to think this way and then be able to contribute to a project.
Not all physics are bad.
No, I'm saying, well, okay, so not all, but I am going to say the way you think and the way they train you as a physicist is opposite of system engineering, and you have to rethink yourself. And everyone in the physics group will think you have lost your mind, okay, by thinking this way. But in the end, you know, you have to be diplomatic, okay? But in the end, I think you can add real value. But it's really, you know, my view, thinking different ways. So yeah, so I've actually spent a lot of time and tried to understand this and present this. I hope that helps. And yeah, I'm sure there's much more to learn than what I showed here.
Yeah, thanks for the talk. I'm just wondering what if you think that it would be useful in sort of other academic contexts beyond quantum computing, if you think that these areas could also gain from system engineering, or you mostly see this as something useful for quantum computing?
Yeah, thank you. I think these system engineering concepts are true for any kind of scientific advance, and you want to take it to the marketplace and start a company, which is, you know, happened a lot here in Boulder with the various technologies. And if you want to go out and work for industry, these are the kind of concepts that you're going to need in industry. So you know, my guess is maybe not all of these things, but generally, if you go and work for a product-oriented company, or I don't know, you're building rockets for SpaceX or something, you know, you're gonna want to be able to think in this way, is my understanding. Now, I think you can kind of get away with it in academia because, you know, you're doing knowledge and whatever, but to really go the next step, which is really hard, going from an academic result to a useful product, that's a hard step. I think this will help you do that step. And that's one of the reasons I like talking about this, because I think for some subset of, you know, most students, you can't become a professor, right? It's really competitive. It's not a huge number of jobs. You'll go off in industry. And I think that this could help you when doing that. Okay.
Why don't we all thank John for a wonderful talk?
Thank you.